Assalamu alaikum everyone. Today we have to continue with this chapter number 11 and we will try to solve one more example to just have a practice on how we can use the heuristics to solve some pumps and vessels and the distillation columns. So I have chosen one exercise problem and we will see that how we can actually solve this problem by using some of the heuristics. Okay, so the question here for the ethyl benzene process as shown in the appendix B. So there is an ethyl benzene process which is given in the appendix B of your book. Check the design specifications for the following three pieces of equipment against the appropriate heuristics: pump PZ301, vessel 302, tower 302. Comment on any significant differences that you find. Okay, so this is the problem statement that we have, and we will apply the heuristics on the pumps, vessels, and the towers, and we will see that how much closer results we can get by applying the heuristics. Okay, now let us see what we have here. This one is ethyl benzene production process, in which we can have the benzene here and we can have the tall ethylene here, and these two components, they react together and then they get separated in the vessel, and we can have two distillation columns here, and we have to use this process and we have to apply the heuristics on some of the equipment. Now the first equipment that we have to deal here, it is the pump 301 here, so we will talk about this one. Then we will talk about the vessel V302 that is given in the problem, and then we will try to solve the tower here T302 by applying simple heuristics. Okay, now let us start with this one, the pump 301, and let's see what we have in the heuristics. Okay, now let us see this solution here. For the ethyl benzene process shown in the appendix, we check the design specifications for the following three pieces of equipment against the appropriate heuristics: P301, B302, and Tower 302. Comment on any significant differences that you find. Now here we are provided some of the information about the pump 301. Okay, from table B dot 2.3. If you go to the table B.3, you would find the following information. So if I take you here, okay, so this one is the table B2.3. So we will go down here for the pump section, and here you would find some of the information on the pump. Positive displacement, this is a type of pump. Carbon steel, it is material of construction. Actual power is 15 kilowatt, and the efficiency of the pump is 75%. So this is some of the information that is already provided to us. So we will put this information here in this form. Now we have to apply the heuristics and we have to find out that what is the actual power required by this pump by using simple heuristics. Okay, so we can go to the table 11.9 which is given to you in the slides of the chapter 11. So the heuristic number 1, we can see here, power for pumping liquids kilowatt, 1.67 multiplied by flow rate multiplied by delta P, and you would get the value for the kilowatt, value for the power in the kilowatt, and the fractional efficiency you have to consider the table 11.5. However, the efficiency here, it is already provided to you, which is 75%, so we are going to directly use this one. So simply what we are going to do here, power for pumping liquids in kilowatt. This is the same equation in the heuristic number 1 as I mentioned here. Fractional efficiency, it is given here 75%. Density of benzene, you can find it from the literature, it is 875 kg per meter cube. Mass flow rate of benzene through the pump. Now we have to calculate the mass flow rate of the benzene through the pump. So we are provided the stream information in the table 3.1. So you would go back to this appendix and you would see table 3.1. Okay, 2.1. Here you would go to the stream number 3, which is about the benzene flow rate. So in kg per hour, that is 17,952. So you have to put this one here, 17,952 kg per hour. That is the benzene flow rate into the pump. Now the flow rate, once you have this one, what you can do, you can convert this mass flow rate into the volumetric flow rate by simply dividing it with the density. So the value for the volumetric flow rate, it would be equal to 0.342 meter cube per minute. Now you have the information about this flow rate for this equation. The next thing, you have to calculate the value for the delta P. So you have to see what is the delta P within the pump. So for this thing, you have to go back to this table here, and you would see that what is an outlet pressure here, that is 110 kilopascal. So 110. Okay, so this is basically the inlet pressure, and what is an outlet pressure, that is given to you in this table. Okay, now for the pump 302. Okay, so if you go back to this figure here, if you look at this pump here, okay, so and on this frame you would see this pressure here, that is 2000 kilopascal. So we have to use this pressure as an outlet pressure and the stream number 3 pressure as an inlet pressure. Okay, now here you would use the outlet pressure that is given to you on the process flow diagram, and then this is the inlet pressure of the stream number 3 that is given to you in the table. So the delta P for this example, it is 18.9 bar. Okay, now this one is the actual delta P that we get from this data here. However, we need to consider that what should be the delta P that we can actually get from the heuristics. Okay, now here 1.67, it would be coming from here, from this equation. 0.342, it is the flow rate that we have just calculated here, and this one is the delta P that we calculated here. So the theoretical power requirement by this pump, it would be 10.8 kilowatt. Okay, and now we have to use the efficiency for the pump that is provided to us, which is 75%. So now we can divide this term with the 75.75. So we can divide this one 10.8 with 0.75, that comes out to be 14.4 kilowatt. Okay, now this is the same power that is provided to you in this example here. If you go back to the pumping section again, okay, now here you can see that what is an actual power, that is 15 kilowatt. So in our example we have got around 14.4 kilowatt, which is quite close to the actual power. So we can say that our heuristics, it can give you the very close results. Okay, so these results are also acceptable from the design point of view. Okay, now let us solve the part B of the question, which is about the vessel 302. Now let us see where we have this vessel 302. So basically it is giving you the information about this vessel V302. So we are provided with this inlet pressure, and we are provided with the outlet stream 15. It could be in the vapor phase, and then we can have the stream number 16, which is in the liquid phase. And you can see here that the 16 number stream, it is being fed to the next tower. Okay, so we have to see the appropriate heuristic that we can apply to this system. Okay, now let us go back to the solution here. V302 from table B 2.3, we can see this one, carbon steel. The material of construction, it is carbon steel with the stainless steel demister. Vertical, uh, the length to diameter ratio is 3. The volume of the vessel is 10 meter cube. Maximum operating pressure, it is 250 kilopascal. Okay, so you can go back to this one, table 2.3, and here you can actually find out the values for all of this one. Okay, so let us see where we have the vessel here. Okay, now here vessel 302, you can see this one, carbon steel with the stainless steel demister. Vertical length by diameter ratio is 3. Volume of vessel is 10 meter cube. Maximum operating pressure, it is 250 kilopascal. Okay, now we can see here that from table 11.6, the heuristic number 4. If you look at this table, heuristics for the process vessel, for the stream number 4, for the heuristic number 4, optimum length to diameter ratio it is 3, but the range 2.5 to 5 is common. Okay, so this one is an acceptable range here. So optimum length to diameter it is 3, but the range is 2.5 to 5, which is common. Use L by D, which is equal to 3. Now let us see some of the more heuristics in this regard for this vessel. From table 11.6, heuristic number 5, hold up time is 5 minutes for half full reflux drums and gas liquid separators, 5 to 10 minutes for the product feeding another tower. Now in this example, what you can see here, we have to consider the condition number 2, because the vessel it is giving the feed to the next distillation column. Okay, so we will use the second heuristic here in this example. Hold up time is 5 minutes for half full reflux drums and gas liquid separators, 5 to 10 minutes for a product feeding another tower. Since liquid by vapor separator feeds to the tower, use a hold up time of liquid equal to 10 minutes for the half full drum. Okay, so we will use the upper limit here for the 10 minutes because the feed is getting entered into the distillation column next to the vessel. Okay, now properties for the stream number 15. So if we look at this figure again for more clarity, okay, so we have this figure. Now you can see this vessel here, and the stream number 16 it is being fed to this column, and the stream number 15 it is directly going as a fuel gas. Okay, so we have to consider this system here, and for this system what we can see here, we have to see the condition in the stream number 15 and the 16. So if you can see here, properties of the stream number 15, the flow rate you can get from the table of the material balance. So you can have the information on the vapor flow rate, which is 103 here. Although this value is different, the actual flow rate is high, so you can see the actual number from the tables. Similarly, the properties of the stream number 16, liquid state, so you can have the information about this stream number 16 from the table. Okay. Similarly, the density, how you can calculate this one. If we take you back here, okay, now here the stream number 15 here, it can show you 1042 kg per hour. So you have to see this one, what is the mistake here. For the stream number 16 it is 24,345. Stream number 16 it is actually equal 24,345. Okay, so now you can use you can calculate the density of these streams. So you are provided here the molar flow rate of each of these streams. So you can calculate what is the maybe the mass flow rate in terms of kg per hour. Then you can calculate what is the mass fraction. You can multiply that mass fraction with this string. Okay, and then you can actually estimate what is the density or the average density of the fluid that is in this string. Okay. Now, once you have the value for the density for both of these streams, you can multiply this one with the vapor flow rate to get the value in terms of volumetric flow rate. Okay, so you have the value for the volumetric flow rate. Now, the important thing here, because the stream number 16 it is getting connected with the next column, like in this example. Okay, so this stream is getting connected with the next tower, so we have to use the information of the stream number 16 in terms of calculating the liquid holdup that is required within this vessel. Okay, now here the vessel, how you can calculate the total volume. So we are provided with this value, the volumetric flow rate for the stream number 16, and we can see this one. What should be the value for this one? For this product feeding another tower, it is 5 to 10 minutes. So we have to see what is a 10-minute liquid hold up time and what should be the volume required in the drum, and then how we can actually estimate the total volume of the drum. So this one 29.64 divided by 60, so we have converted this hour into the minute, and then we multiply this one with the 10 to get the liquid hold up required for 10 minutes, 10 minutes of the flow. And then we have seen that this is in the information required for the half full reflux drums. Okay, so we have to consider the other half of the drum also to consider to estimate the value of total volume. So we can either divide it with the 0.5, or you can multiply this thing with the 2. Okay, so the value for the drum of the volume of the drum, it comes out to be 10 meter cube. Okay, now we can say this one. If you go back to this table here, the value for this drum here, now here you can see this one V302 vessel. The volume of this vessel, it comes out to be 10 meter cube, and in our example or in our calculation we also get the exactly the same volume of the drum. So good agreement with the heuristic. So we can see that how we can actually use this simple heuristic to calculate the volume of the drum. Now let us solve the last equipment in our today's example, which is the Tower 302, which is the distillation column. Okay, so we have to see this column here. So we have to calculate the heuristics or the size of these this column in terms of reflux ratio, minimum number of trays, and what is the length or diameter of this distillation column. Okay, so we will use simple heuristics again to estimate what is the critical information we can actually find out by using the heuristics. Okay, now for the tau 302 carbon steel, so maybe you can go back to the information on this tower P302, which is provided here. Now here you would go to the table 2.3, and here you would find the tower information on T302, which is the carbon steel. There are the number of trays here, 76 stainless steel, C trays plus V-boiler and total condenser. 45% efficient trays. This is the efficiency of each of the tray. Feed is on the tray number 56. Additional feed ports on trays 50 and 62. Reflux ratio, it is provided here 0.6608, and we will see how we can actually cross check our values when we calculate the reflux ratio by using the heuristics. The tray sizing, it is spacing between the trays, it is 15 inch. The column height, it is 28.96 meter. The diameter, it is 1.5 meter. Maximum pressure rating of 300 kilopascal. Okay, so we have provided some of the information on the column height, diameter, operating pressure, the distance between the trays, and the reflux ratio, and we will see that how these results can be compared with our heuristic results. Okay, so let's go back to the solution here. Now from table 11.13, this is 11.13 table, and 11.14 in continuation to this table. Optimum reflux is in the range of 1.2 to 1.5 R minimum reflux. So you can see this one, rule number 5 here. Economical optimum reflux ratio is in the range of 1.2 to 1.5 times of the minimum reflux ratio. Okay, so we can use this heuristic here. If we slightly go down here, optimum number of stages approximately 2 multiplied by n minimum, which is the minimum number of stages. So the economical optimum number of theoretical trays is near twice the minimum value n. Okay, so we can write in this one 2 multiplied by n minimum. Heuristic number 7, and minimum number of stages, it can be calculated using this Fensky's underboard equation. So we can have this value here. We have this equation here, log x divided by 1 minus x, and so on. Okay, and this one alpha here, we can see this one. It gives you the information about the relative volatility. So you have to find this alpha by yourself. Okay, and this one, the x represent you what we have in the process, which is the ethyl benzene. Okay, so we have to calculate or do the calculation with respect to the ethyl benzene in the overhead stream and in the bottom streams. Okay, Now, rule number 8, R minimum, it is equal to feed divided by display divided by alpha minus 1. So we can have this equation for the R minimum. Okay. Then rule number 9, use a safety factor of 10% on number of trays. So you have to use the safety factor as given here in the rule number 10 to be on the safe side. Table 11.14, rule number 2, f of s u rho v 0.5. So you can go to this table 11.14 and here you would find this equation. Peak efficiency of trays is at the values of vapor factor. So you have to calculate this vapor factor fs, that is equal to velocity density for the vapors, and with the power 0.5 and in the range of 1.2 to 1.5 meter per second. Okay. So you can write down this equation in the form of, instead of this velocity, we are provided with this value 1.2 to 1.5, and just we need to have the value for the density for this vapor. So we have to calculate the value for the density of vapor and then we can find out the range of the velocity. Rule number 4, efficiency of trays, it is between 60 to 90%. Okay. So rule number 4, here it can tell you the efficiency, it can vary between 60 to 90%. However, in this table B2.3, we are provided with the efficiency of the phase which is 45%, so we have to use this value. Okay. Now for our case, this is the information that is provided to us. Stream number 18, 19, and 20. Okay, for this flow sheet, we are provided with the information on the stream number 18, 19, and 20. So we are talking about this column. So the information on 18, 19, and 20, it is provided to us here. Okay, so we will use this table for our further calculations. Now key components are ethyl benzene and 1,4-diethyl benzene. So if you go back to the flow sheet, you would see that in this distillation column, we are separating the ethyl benzene from the 1,4-diethyl benzene. Okay. The formula for minimum number of stages should be based on these components using as a benzene free basis. Okay. On the basis of benzene, we would calculate the minimum number of stages. Now to get the value for this overhead, the mole fraction of the benzene in the overhead stream, you would use the equation here. This one, okay, 89.72 divided by this one total value. So you would get the amount of ethyl benzene in the overhead stream. Similarly, you would find out the value for the ethyl benzene in the bottom stream, and then using the volatilities and of each of the component and using the Antoine equation, you can get the actual value for the pure vapor, the pressure. Okay, you would use the Antoine equation. You are provided with the temperatures here. Okay, so you can use this temperature equation to get the value for the pure vapors. Okay, and from there you can get the value for this alpha overhead and alpha bottom. Okay, so you must have studied this thing in the stage-wise distillation process also. Okay, so you can use this equation here to get the value for this average, average relative volatility, which is alpha overhead multiplied by alpha bottom with the power 0.5. So the value for this one, alpha for the average relative volatility, it comes out to 3.50. Now we have to calculate the value for the minimum number of stages. So how you can calculate this one? We have to simply use this equation, Fensky-Underwood equation. So we were provided with this equation here. So the value for this x you would be getting here from the overhead stream, and similarly here you would get the value for this bottom stream. Okay, and the alpha value you have just calculated here. So the minimum number of stages with the full reflux, you can have 12.9. Now you can estimate the value for the minimum reflux ratio by using this equation simply. Okay, RD, this equation, F by D. You can rearrange this equation basically. Okay, to get the new equation, F by D, which is provided to us here. Okay, F by D alpha minus 1. So you can use this equation. So you know what is the value for the feed stream, inlet stream, what is the value for the distillate stream, then you have the value for this 3.5 alpha minus 1. So the minimum reflux that you can calculate here, it could be 0.453. Okay, so once you have the value for this minimum number of reflux, then you have to use this rule number 5, which is here 1.2 to 1.5 times of the minimum reflux ratio. So you have to multiply this number with 1.2 to 1.5 to get the range of the reflux. Okay, that comes out to be 0.544 to 0.680, and if you go back to the table that is provided to us, the table, if you go back to the table 2.3 here, as I mentioned earlier, so the minimum reflux that is mentioned here, it is 0.6608. However, in our example, we get it in the range of 0.544 to 0.680. So this is within the range here. So our estimate is good enough. Now we have to estimate the number of theoretical stages, which is 2 times of the minimum number of stages that we have calculated here. So we can simply multiply this one with the 2 to get the number of theoretical stages. The tray efficiency, it is mentioned in the table, it is 45%. You can see this one. Okay, now you can divide this one number of trays with the trays efficiency, and then we can multiply this one with the 10% additional factor, and that number of trays that we find out for our example, it is 63 trays. However, in this problem it is mentioned that the number of trays, these are 76 trays. Okay, so there is a difference of 13 trays. Now we will see that why there is a high difference at the end. Okay, now we have to estimate what is the diameter of the tower. So we have to first calculate what is the density for the vapors. Okay, so you are provided with the component flow rates, and then you can get the value for the mole fraction, and using the molecular weight of each of the component, you can actually get the value for the average density for the vapors. Okay, so that comes out to be 3.71 for this problem. Now if you go back to this table here, 11.4, where we have to calculate the vapor factor. So this range, it is from 1.2 to 1.5. So 1.2 to 1.5 divided by we can have the density of the vapor 3.75 with the power 0.5. Okay, so the range for the velocity, it comes out to be 0.68 to 0.78 meter per second. Now the vapor flow rate that we get from the stream number 19, it is equal to 9539 kg per hour. Similarly, the volumetric flow rate, once you have the density here, you can get the value for the volumetric flow rate, and using the equation for the mass flow rate, you can convert the volumetric flow rate into the velocity and the cross-sectional area, and rearranging the equation, you would get the equation in terms of diameter of the tower, and you can solve this equation to get the value for the diameter of tower, that comes out to be 1.08 to 1.21 meter. And from the actual results, we have seen that the actual diameter, it is 1.5. Okay, here it is mentioned that the diameter is 1.5. In our case, we get it from 1.08 to 1.21 meter. Okay, now some of the results, these are in good like agreement with the heuristics and the actual result, but some of the results are fluctuating. So we will see some of the reasons here. Overall, for tower 302, the agreement with the heuristic is fair. This is probably due in part to the use of fairly low reflux ratio that is at the bottom of the typical range given in the heuristic. So you can see this one, the range for this minimum reflux we are getting from 544 to 0.68. So if you are using low value for this reflux, then you have to increase the number of stages. So this is one of the reasons. This tends to increase the number of trays. In addition, the tray spacing in the tower is only 12 to 15 inches. Okay, so this is another reason. Usually, the tray spacing between each other, it is from 20 to 24 inches. Okay, so if you go back to this heuristic number one, okay, for the reasons of accessibility, trace spacings are between 20 to 24 inches. Okay, so this is one of the reasons, because if you are using the low number of if you are just minimizing the spacing between the trays, then the chances of the flooding would increase. Okay, so this is one of the reasons that you can have more number of trays in the same column. This has the effect of reducing the tray efficiency and requires a larger diameter column to stay away from the flooding. These differences probably account for the discrepancies in the above results. Okay, so these are some of the reasons that can answer why there are slight variations from the heuristic results, and why there is some slight difference in the values from the actual results. Okay, so if you don't understand anything, please let me know. Thank you.